So on this trolley, which is deliberately positioned away from our experimental setup, such that we can see the front panel from the control room through a glass window, is our acquisition system. And here you can see we have multiple sensors connected into the acquisition front system front end onto an input module. So we have our 2 laser vibrometers coming in on channels 1 to 4, and I'll show those in more detail. We have, I believe, our torque transducer connected into channel 5, and we have our 3 accelerometer directions onto channels 6, 7 and 8 of our acquisition system. The encoders are connected via these 2 connections here, which are a mil-spec connector into a separate input module which provides the power for the encoder and also allows the conversion of the various pulse train signals into rotation speed and angular position. There are some additional input channels here that are available for use, particularly a couple of tacho channels which we can use. We can also use this system to generate an excitation signal if we wanted to use it, for example, for experimental modal analysis. It can drive 2 electrodynamic shakers with, for example, random noise signals. We have an Ethernet cable which allows us to connect it to our host PC where we control it. There's also a CAN bus in here, so we can connect it to the CAN system for example, automotive testing in vehicle. And so then moving further down here, I mentioned the laser vibrometers which are connected onto these first 4 acquisition channels. Now these laser vibrometers will give us an output of delta omega, which is the angular velocity. They can also give us a second output, which is simply an integration of the angular velocity signal called delta phi, which is an angular displacement. We're not using this because we can do that integration in post-processing ourselves if we wish. So we only take angular velocity signal, which is the primary measurement. We can define the sensitivity of the angular velocity signal and change that using this. So for more angular velocity, if we had lots of angular velocity, we would deliberately choose a higher sensitivity. If we have less angular velocity, we can reduce the sensitivity of the instrumentation. You can see that we've turned off the delta omega there if we go for the higher rate. When we use 100 degrees per second per volt, our sensitivity for displacement output, if we were using it, would be 1 degree per volt. So these engineering units here of degrees per second and per volt we will make use of in our acquisition system. We also get a reading of the RPM, like of the DC signal. So as well as measuring the angular velocity, we're also measuring the mean speed, and the mean speed output is available to us. And this, once the system is rotating, will have a non-zero value, and that RPM signal is coming out in a voltage or proportional to voltage via this signal. So we can also measure the RPM in our acquisition system.